Good morning, everyone. So just a quick announcement. Um, I put the solutions to assignment 1 on the website. Was it this morning? Must have been this morning, yes. So I'd like everybody to read it and mark their own homework and assign yourself a score and email it to me. So Michael and I will sample grade some questions from your actual homework, and we'll look at what you've assigned and choose what's the actual thing to enter on my courses. Okay, so this way, Michael is not having to grade all these things so quickly. Right. Secondly, have I turned on recording? Yes. Secondly, I am going to ease the pace a little bit. People are, well, my friends rather than my students are telling me I'm going at an intense pace. So today I will actually begin with material that probably half of you know really well, but maybe half of you don't know at all. And that is basic logic, because I was supposed to do temporal logic. And then I realized some people don't know words like soundness, completeness, etc. This word completeness is super overused in mathematics. It means one thing in topology and one thing in functional analysis and another thing in logic. So I'm going to start with basic propositional logic, but not, very elementary stuff. I will try and highlight the main theorems and not prove them, but there's some words that you ought to understand. Dragos, you start asking questions about the assignment later, not in the middle of the class. Thank you. Okay, so let's begin. So I want to talk about basic propositional logic.
Oh gosh, I think you need a screen share.
I do what?
You need to screen share.
Oh yes, darn it. Thank you. One day I'll get this right. Share. Okay. Screen mirroring. There we go. Come on. Hello. Okay, good. Basic propositional logic. Now, basic propositional logic, all of you know. In fact, all of you know first order predicate calculus even. But what you probably don't know is meta theory about it. And so I'm not going to sit down and explain how you model John and Anne went to the shop to buy groceries in propositional logic. I will rather tell you the meta theory, the grand theorems about propositional logic itself. And the reason I'm choosing propositional logic is simply because you do all know it. So you can relate to the meta theory immediately. There is a great deal of confusion, I find, in people's mind, unless they've studied logic formally, about what is meant by a true statement, what is meant by a valid statement, what is meant by a theorem. These are all different things. And the relationships are quite tight, but they need to be spelled out. And the reason I need to do this in this elementary setting is because I'm then going to throw you into temporal logic, which is an unfamiliar logic, and you should understand the difference between the proof theory and the semantics. Okay, so ready to roll? Here we go. So first we define what are formulas, and we start with a countable set, which we'll call prop, and we'll use letters like this. These are the propositional variables. Okay, and then I will use Greek letters as meta variables. So these are not variables. Phi and psi are not part of the notation of propositional logic. They're part of the language that I am using to talk about propositional logic. So propositional logic is itself a language, and I'm explaining aspects of that language to you. The language in which I'm carrying out that explanation is kind of half English, half semi-formalized mathematical notation. So phi and psi are those languages, those variables in my meta language so that I can talk about generic propositional formulas. So now I will say, so meta variables standing for propositional formulas. Okay, so in logic books, they often use this phrase well-formed formula, and they even pronounce it woof, which sounds a bit like a dog barking in the night, but I don't understand what's meant by a badly formed formula. If it's not well-formed, it's not a formula. So I just call it formula. So formulas are defined inductively. And this pattern persists in propositional logic and other logics that we are going to define. I have actually prepared handwritten notes, scanned them and put them on the website. So they're there. Okay, so how would we define these things? So first we'll say T is a formula. So this is just a special constant. Secretly it stands for true, but what I want to emphasize at this point, these things are not interpreted yet in any way. So don't keep asking me, what does this mean? What does that mean? They don't mean nothing. They're just notations. When we explain what they mean, that is called semantics. And I want to separate the semantics from the syntax from the proof theory. What I'm telling you now is syntax. Just what am I legally allowed to write? I'm no way explaining what these things mean. Of course, these are familiar notations. So in the back of your mind, you know what they mean. Any propositional variable is a formula. If phi is a formula, so is not phi. So this is what I mean by inductive. You've got some formulas and you give rules for building new formulas from old ones. If phi and psi are formulas, so are phi and psi, phi or psi, phi implies psi, and there could be more things, but let's stick with these. Okay, so that's it. That's the end of syntax. So now you can write down a bunch of formulas like P and Q or R implies T or something like that. And just by successive applications of these inductive rules, you can write down the collection of all formulas. Of course, it is an infinite set. Okay, so this is just syntax. Just because these are familiar things that you understand, stand for the usual symbols for and, or, and implies, does not mean that I have yet interpreted them. So now when it comes to interpretation, two things happen simultaneously. So and I think what often happens when people just kind of learn mathematical notation without taking a formal logic class, they confound these two different explanations. So I want to show you these two explanations are very distinct and then prove to you theorems that say, yes, they might be distinct, but they're very tightly coupled. So the first explanation is called proof theory. And this is about how to use and manipulate formulas in a process called deduction. Okay, so the basic unit of deduction, so proof theory for logics can be presented in a variety of ways. There's something called sequent calculus, there's two-sided sequence, there's something called natural deduction, there's something called Hilbert style axiomatization, which I personally hate. So I'm going to show you a kind of way of presenting what's called natural deduction. And what's cool about natural deduction is that it's very natural. So there's going to be a basic form called a judgment. A judgment has this appearance, where this is a set of formulas can be infinite and a single formula. And the intention of this judgment is if I use the elements in gamma as assumptions, I can prove phi. And how does this proof process work? So there are rules for constructing proofs. So these are called rules of inference. And these rules are all about constructing proofs. I still haven't told you meaning. What does a formula mean? I have not told you anything about it. You can think of proof theory at this stage purely as a formal game whereby I'm manipulating certain things. So what are these rules? They have the following format. It says, if I have some judgments that have been established somehow, okay, so from gamma 1, maybe I constructed a proof already of this, and then this, and this, and this. So I've somehow established all these judgments. Then I can conclude some other judgment. So this is not a rule. This is the format of a rule. The thing above the line could be empty. And when it's empty, it's a special kind of rule called an axiom. Does not require any hypothesis. It's just unconditionally true. Now in Hilbert style axiomatization, they'll write down just the proof doesn't look like this. It's just a sequence of lines. And on each line, there's some formula. And then there's some rule that says you can transform one formula into another formula by using one of the rules. And then your proof just looks like a line. But our proofs are going to look like trees. Okay? The leaves of the trees are axioms. And we are just going to have one kind of axiom format. It says, without any assumptions, you can assert that gamma proves phi precisely when phi happens to belong to this set. So if phi is one of your assumptions, well, sure, you can prove it. Okay, and that is to me the simplest axiom. In Hilbert style presentations, you'll see there's 17 formulas they write down and they'll say, these 17 things are axioms. And you go like, how did you choose these? Like what? But here it's kind of obvious. There's only one axiom and it says, if you've assumed something, then by golly, go ahead and say, yeah, I've proved it from this assumption. Now, of course, what we're interested in doing is ultimately proving judgments in which there's no left-hand side. So some of the rules are actually going to get rid of assumptions. And in the end, if we can successfully get something that has no left-hand side and just a formula on the right-hand side derived from axioms and using valid rules, then that thing is called a theorem, something that you have proved. I still haven't used a word that's probably burning in your mind, which is called true. I have never said anything about anything being true or not true. Proof theory is not about truth, it's about proof. Semantics is about truth. Okay, so let me show you the rules. So here is a rule. The first rule is called weakening, and it's so basic that I forgot to put it on the sheet. And it says, if from gamma you've managed to prove phi, then if I add more assumptions, it doesn't stop me from proving phi. So it's almost like a monotonicity property. So it says you can weaken your result by adding new unnecessary hypotheses. Okay, so this just means, so strictly speaking, I should write gamma union this because I said gamma is a set, but we write gamma comma psi rather than this. Okay, but it should be interpreted like that. All right. So that is what's called a structural rule. It doesn't talk anything about the actual so-called logical connectives that we introduced in our inductive definitions, the and, the or, the implies. Oh, I forgot one important thing, a super important thing. True is a formula, and this thing is a formula. So that bottom symbol stands for false. Backslash POT in LaTeX. Okay. Now, the rules tend to come in pairs, nearly all of them. And one set of rules are called introduction rules. The other set of rules are called elimination rules. And they're called that because one set of rules introduces the logical connectives. The other set of rules gets rid of them. So we organize the rules into two sets, intro and elim. And for each connective, almost every case, not exactly all of them, we'll have a matched pair. So the most basic one is the rule for and. So if I've somehow proved phi 1, and I've also proved phi 2, possibly with different assumptions, then if I combine my assumptions, so here again, writing gamma 1 comma gamma 2 actually should be the set union of those two sets of assumptions. But it's traditional in logic to write it. So you don't need any notion of truth to see that this corresponds to your intuitive idea of how and should be used. And you see there was no and above the line, and it has appeared below the line. That's why it's called an introduction rule. An elimination rule looks like this. If I've somehow proved phi 1 and phi 2, then I can just say, well, I only need phi 1, or I only need phi 2. So it's legitimate to just discard some of the things that I proved if I decided I don't need them. So these are called elimination rules, and there's a pair of them. So it tells you I can discard either one. I'm going to go to speaker video, active speaker. Okay, the second most important connective is arrow. And this says, the introduction rule says, if one of your hypotheses is phi, so this way of writing it says there's some set and included in that set is phi, and the rest of the thing I'll call gamma. If with all this I've been able to prove psi, then I can get rid of phi as a hypothesis and replace the psi by the contingent statement, phi implies psi. And how I use arrow is like this. If I've somehow proved phi implies psi, and elsewhere, perhaps with different hypotheses, I've proved phi, then I can conclude psi. Okay, so this looks exactly like what you would intuitively expect implication should really mean. You've proved that phi implies psi, and then you go ahead and prove phi. Well, then psi follows. None of this rubbish about truth tables and weird entries when both of them are false and stuff. For or, it's the intro rule is very easy. The elim rule is a bit subtle. So if I've proved phi, then I've kind of automatically proved phi or psi. Because phi or psi just says prove one of them. Well, I've already proved one of them. So nothing stops me from asserting the elimination rule is a bit trickier. So it says, look, you've proved phi 1 or phi 2. And then with some assumptions and phi 1, you've proved psi. Also, with some other assumptions and phi 2, you've also managed to prove psi. So then basically you've said, well, maybe I'm not sure if I proved phi 1 or phi 2, but somehow I've got the cases covered with this one. So I can combine the three of them and say, okay, if I combine all these assumptions, I can prove psi. And this is or elimination. And finally, for the bottom, there's simply a rule like this that says, if you prove bottom or falsehood, then you can prove anything as a consequence. And we will view negation phi. I'm not going to write down the rules. I've written some rules on the sheet, but this is just a macro for phi implies bottom, which is what not phi should mean. If you assume phi, then you'll derive a contradiction. So that means phi better not be true. But that truth notion is an informal statement. These proofs are just formal things. No interpretation is intended at this stage. And finally, I want to write one special rule. So special that I'm going to write it in red. So this one says, if you have somehow proved not phi, then you can prove phi. So this is called double negation. Okay, so intuitionistic logic rejects this rule. But even though I'm a big fan of intuitionistic logic, and I personally consider it the one true logic, I'm going to teach you classical logic because that's what the rest of the world seems to like. Okay. In my notes, I've given an example of a proof that you build within this logic. So let me just introduce some terms. A proof is a tree whose leaves are axioms. The nodes are rule instances. And the root is a judgment is a single judgment. If the root has the form, i.e. nothing on the left-hand side, we say phi is a theorem. And propositional logic is extremely elementary, but you can enrich it to make first order predicate calculus. You can enrich it to make it second order predicate calculus. You can enrich it to become arithmetic, etc. These words and concepts are all the same. The rules, of course, are different and enriched. All right. So here's I'll give you a very short proof. There's a slightly longer proof in the notes. So from assumption P, I am able to prove P. Wow, that's an axiom. Then using arrow introduction, I can prove P implies P. And by golly, P implies P, this is a theorem. And you might think that's not a very exciting theorem, but we have to start small. Keep going and you finally get to Andrew Wiles's theorem. Okay, so all this while I have talked about syntax, and then I talked about proving things, which is essentially structural modifications of formulas according to rules until you arrive at what you can call a derived rule. And finally, we're going to talk about the third branch, which is semantics. And this is a completely different branch. But the fact is the two branches are so tightly tied together that people are confused about the difference. So we are now going to interpret logical formulas as elements of a simple mathematical structure. And what is this mathematical structure? It consists of two elements called true and false. This is the two-element Boolean algebra. And this is equipped with some operations. And these operations, coincidentally, but not so coincidentally, have the same notation as the symbols we introduced in our proof theory and syntax. Okay, and you can introduce the arrow as a derived operation. All right, so what these operations mean, you know very well, defined by their usual truth tables. Okay. Now we will define something. So if I ask you, is P true out of the blue? Oh, this doesn't make any sense. If I ask you, is P and Q true? It doesn't make any sense. What are P and Q? It's just uninterpreted symbols. So in order to make sense of a complex formula, I need to assign truth values to the atomic formulas or to the propositional sentences. So evaluation V is a map from the collection of propositional variables to the two-element Boolean algebra. Sometimes people write true, false. Sometimes they write 0, 1. Sometimes they write the true and the false sideways. And there are actually interesting reasons for all these choices of notations, but let's not worry about that. Right now, it's just two things. We know that that two-element set is equipped with some operations, some unary operations like negation, we just flip them, and other binary operations whose truth tables you know very well already. And then we extend V to a map on formulas by structural induction. So what does this mean? We've given you, well, first we'll say the valuation of true, the capital T symbol is not a propositional letter, it's a constant. And the valuation of bottom is always false no matter what you do to the variables. And then if I've given some valuation to phi and I've given some other valuation to phi prime, then this defines the valuation of phi and phi prime. But very important, this is the Boolean algebra operation. And this is defined in the syntax. So it may be confusing to you that we use exactly the same symbol because we're so familiar with it. Perhaps if I had used like this for the syntax and this for the semantics, it would be clearer that these are different things. But it's now so ingrained in us to use this in both ways that it's conventional to say, well, when we write it here, we mean the Boolean algebra operation between truth values. And when we write it there, we just mean the logical connective between formulas. And the point is that is indeed interpreted this way. Okay, so is everybody clear about the distinction between syntax and semantics? Now I'm going to introduce a new symbol in LaTeX. This is /models, emphasizing its model theoretic roots. Now, this means something very different from this. This means from assumptions and using rules of proof theory, I can derive this judgment. This means something about truth values. Okay, so that's a parenthetical remark. So what does this mean? If V has the property that for every formula in gamma, V of psi is true, then it must hold that V of phi is true. So any valuation that forces everything in gamma to be true will also force everything in phi to be true. Well, not everything in phi. Phi is one thing. Will force phi to be true. So this thing is called entailment. Okay? If this thing holds, then it means unconditionally for every V. Now there's no requirement on making anything true because there's an empty set here. For every V, V of phi has to get the value true. Such a formula is called a tautology. Okay, tautologies are not the same things as theorems, but in fact, now prove, or we don't prove, but we state two important theorems. So first theorem is called soundness. Okay, and soundness says if you're able to prove a judgment like this, then this holds. And the truth values line up exactly the right way. Stated, so in particular, a special case is that if phi is a theorem, then it must be a tautology. What this says is the things that you can actually prove with your framework are actually true according to your notion of truth. And if you have a proof system without this property, it is worth zero. In fact, it's worse than worth zero. It is downright harmful. So soundness is a fundamental property. It has to be there in any logical system. If you don't have it, throw it away. There's no use for it. You might ask about the converse, and that is a very important property called completeness. Don't confuse this with completeness of metric spaces or anything. This says if a judgment is actually true, then you can prove it. So this says your proof system is rich enough to prove anything that happens to be true. And now completeness holds for first order predicate calculus and certainly for propositional logic. And if I had a bit more time, I'd actually prove it because it's not that difficult and it's quite interesting. And there's some actual math going on in the proof. It actually uses the axiom of choice, but but it can be proved without the axiom of choice also for propositional logic. But I don't have time to that because I really want to get to temporal logic today and finish it. Kurt Gödel freaked out the mathematical world so this is a very crude rendition of what Gödel actually proved. So by completeness is by no means guaranteed whenever you have any old logic of interest. Okay, so I'm hoping that this now puts into perspective three pillars of a logical framework. What is the notation and what are the valid formulas? Sorry, not valid formulas. What are the well-formed formulas? What are the theorems, i.e. things that can be established by your proof system, and what are the tautologies, things that are true under all interpretations. So tautology means no matter how you interpret it, it is going to be true. Okay. So now is not the time to start talking about intuitionistic logic and why it's so wonderful, mainly because if I start on that, I won't stop. But I'll just say a few more things. Suppose gamma has no valuation such that for every phi and gamma, V phi is true. Then we say gamma is unsatisfiable. And if that's not the case, then we say gamma is satisfiable. And these words apply equally not just to propositional logic, but also to first order logic, where the notion of interpretation is, of course, more elaborate because it's not just truth values now. I have to introduce not just propositional variables, but um, variables that stand for things and build up terms and so on. We'll actually do that later on, but I wanted to give you this warm up. There is an interesting theorem called compactness. If gamma is unsatisfiable, then some finite subset of gamma is unsatisfiable. So basically, if something goes wrong, you've put together too many formulas and start contradicting each other, well, that contradiction will be confined, will already happen at some finite stage. It can't kind of happen in the limit. So this is a compactness property, and it really is tied down to topological compactness. So remark, temporal logic fails this property. Okay. So I've drawn a little roadmap of different kinds of logical universes on the notes that I've posted. You can look at them, but right now I want to get on with temporal logic. And so here the idea is the basic atomic propositions can change their truth values in time. So whereas before we just said, okay, so here is a valuation, P is assigned true, R is assigned false, Q is assigned true, blah, blah, blah. Now work out the truth value of some big monstrous formula constructed out of these things and the connectives. Here we're saying, yeah, but that might be today, but tomorrow the valuation might be different. And temporal logic was kind of a thing that philosophers debated about in the 20th century, but Amir Pnueli showed this is very useful for reasoning about programs. Especially concurrent programs. Okay, so I'm not going to talk about concurrent programs or how this is useful for reasoning about programs, but you can get the idea. We've got some variable x equals, and you might have a proposition x equals 1. But of course, as the program executes, the value of x might be changing. So you now want to state things about the execution of the program and not just what it is in one state. So as the program executes, the state changes and the truth values of things change. And now you want to say things that are modulated by time. So that is the whole essence of temporal logic, to talk about things that execute. And this is, I think, a tremendously useful uh, kind of logic, especially for computer scientists working with program executions. Okay, so I'm going to follow the same paradigm. We'll first do syntax, and then but I'm going to do the explanation of the semantics first, and then I'll write down some proof principles. Okay, so the syntax is like this. You have some atomic propositions, which I'm not going to specify. It'll look just like propositional logic. So in fact, this is kind of like propositional logic with more funky operators than the Boolean ones. And now the formulas. So you have all the Boolean connectives, but let's just take a minimal set. If you want, you can put them all, but we know that we can actually derive them. And then I'm going to introduce two temporal operators. And they are written with a circle and as a big U. Okay, so formal definition, if phi is a formula, then circle phi is a formula. If phi and psi are formulas, then phi fancy u psi is a formula. Okay, so if I write down the whole syntax in more programming style notation, then true is a basic formula. Any atomic proposition is a formula. If I have two formulas already, I can take their conjunction, I can take its negation. If I have a formula, I can stick a circle in front of it. And if I have two formulas, I can stick a U between them. So that is the complete syntax of what's called linear temporal logic. There is another kind of temporal logic out there called CTL, computation tree logic, which I'm not going to explain in this class. They both have their advantages and disadvantages, but I'm just sticking with linear temporal logic. So the whole idea of linear temporal logic instead of evaluation, we have a linear sequence of valuations changing in time. So the valuations change in time. We will call these valuation states. So it jives with our programming intuition that what we're reasoning about is the execution of a program. And as the program executes, the state changes, and we're looking at how the state changes and making statements about the whole history. We'll call these valuations states, and this entire sequence is called a history. Okay. So I'm just going to introduce some defined operators, and I'll give you the semantics of everything after that. Defined operators. So we know that we can define or as the negation of not phi 1 and not phi 2. Okay, and we know once we've defined or, we can define an operator like this as not phi 1 or phi 2. All right, so that's familiar Boolean stuff. What about with the temporal world? So we're going to define a new operator called diamond. So diamond phi is defined to be true, and then this funky U thing until phi. And box will be not diamond, not phi. And the intuition between this is eventually, and the intuition behind this is always. And you can see that these are very temporal concepts, eventually and always. Okay, but now I have to give you a formal semantics. So here is what the formal semantics looks like. So this idea of having a richer logic that captures ways in which the basic notion of truth can be modified is called modal logic. And temporal logic is an example of a modal logic. There are many other modal logics. You'll see some. And in particular, there are logics for reasoning about probabilistic systems, which, for example, I have used in my work. Okay. So remember what one of these histories looks like. There's some state, and in the state, maybe a couple of propositions are true, maybe P is true and Q is true, and then something changes, and then P stays true, but Q becomes false, and then something happens, but none of these things are actually affected by whatever happens. And then maybe P turns false and Q becomes true, and so on. So this is an example of a history. I did appoint a co-host, right? Is that you, Asa? Hello, have we lost Asa?
Yeah, no, sorry. Yeah, that was me.
That's you. Okay, so remember to stop me if anybody has burning questions on the chat.
Yeah, I'm checking.
Good, thank you. Okay, so I'm going to write, so this is an example history. If you were actually applying this to computer science, maybe your proposition P is that X is set to 0, Q is saying Y is set to 1, And then as things go on, these things change. Maybe they become both are true, both are false, etc. Okay, so now I'm going to write oops, what happened? Sigma is a history, and each state in the history will be written like this: sigma 0, sigma 1, sigma 2, and then I'll also introduce this notation. Sigma I with a pair of dots. This is defined to be, you start the sequence from position I. Okay. We always assume these histories are infinite. Towards the end, I will talk about how to interpret these temporal logic formulas on finite sequences, and then we'll connect it with automata theory in regular languages. Okay, so now I have to tell you what is the notion of truth. And the semantics will look like this. So here there will be a history, and here there will be a formula of LTL. And we will say sigma satisfies phi, or sigma models phi. So I'm explaining temporal logic in a very much model theoretic way rather than in a proof theoretic way. Okay, that's just my taste. I could have presented it with proof theory as well. Okay, let's go. So now the semantics is going to be given by induction on the structure of the formula. So I have to start with a basic formula. The most basic formula is the atomic one, true. And now you see why it's a good thing to have a trimmed down syntax and introduce the other things as derived operators, because now I can give the full semantics with fewer cases. So this just holds always. So true means you're saying nothing. Any history satisfies true. Supposing P is just a proposition, then sigma 0 in the propositional sense. So remember what what these states are. They're telling you truth values for all your atomic propositions. So it'll tell you, the explicit description of sigma 0 will tell you, is P true or not? Okay, so basically this means, is P true now? So we should interpret sigma 0 as now. This is what's happening now. Okay, and anytime I make a propositional, so all purely propositional formulas are interpreted this way. By purely propositional, I mean there's no circles and U's and things. All right. Now we need to probe into the future. That's what the temporal operators are for. Okay. So the most basic one is this one. This holds So remember, sigma by itself starts with 0. So this sigma 1 dot dot means instead of starting from 0, you start from 1, i.e. you drop the present valuation and you look at the next one. So the intuition is sigma phi means phi holds in the next step. And we read it as next phi. Okay? And now we come to the tricky one. And this says there exists a j greater than or equal to 0 such that, so this means sometime in the future, I don't know when, maybe right now, because it's greater than or equal to 0. If not right now, then sometime in the future, I'm not telling you when exactly, but sometime, psi will become true. And for all I strictly less than j, notice strictly less than j, sigma I dot dot satisfies phi. So the intuition here is phi holds now and continues to be true continues to be true until psi becomes true. When psi becomes true, we don't care what happens after that. It may or may not be true. We don't care. Nothing is said about it. We don't care about phi at that point. And we don't care what happens to psi after that. Okay, so is this clear? If there's any question about this, so this is read as phi until psi. It may be that psi is true right now. Then we don't care about phi at all. If psi is true right now, that's it. This formula is just true. Whether phi was ever true or will be true, we just absolutely don't care. Also, this guarantees that psi will become true at some point. So you can't say, oh, I've satisfied this by, psi is never true, but at least I've maintained phi to be true all the time. No, that's not allowed. Okay, built into this is the statement, yeah, at some finite time, psi really will become true. So phi is not going to be faithfully guarding you forever. At some point, psi will show up and then phi will take off. So let's look at what happens to the other operators, the derived ones. So just reading the semantics for until specialized to the case. Remember, diamond means true until phi. So that just means, well, true is just always true. There's nothing to check. So what is it saying? It's just saying at some point phi will become true and I don't care what happens before that. So this is, there exists I greater than or equal to 0. So it might be already true now, in which case you're done, or you might have to wait for a while, but you don't have to wait forever. There exists I greater than 0 such that sigma I satisfies phi. And this is essentially the De Morgan dual. For all I greater than 0, so I thought I would give some examples of formulas. So here, let's say we are modeling a system of traffic lights. Now, I'm talking about, normal traffic lights in a normal place, not Montreal traffic lights, which seem to have the most weird behavior I've ever seen. So, so what do normal traffic lights do? Well, you start out red, which means stop. If you're red, maybe the next second will also be red. You don't know. For some time it stays red. Then, does it turn green? No. You always first turn yellow. And then after yellow, you get green. But you know that if you wait long enough, so sometimes you might start doubting it, that eventually it really will turn green. So we want to write down that basic guarantee. It's always true that if you see a red light, at some point, it will eventually turn green. So this is a typical use of box and diamond. Until is super useful, but it's kind of, you start nesting a few untils and it becomes absolutely unreadable. So, so box and diamond are a lot more readable. Sometimes you have to say things with until. And there are all kinds of very interesting theorems proven about the expressive power of untils and so on. But let us just do simple things without too many nested untils. Now, we also know that if it's red, that it implies it's not going to be green in the next state. Why? Because we know it has to go through yellow first. So is this clear? Are both these things clear to everyone?
Shouldn't we do the opposite of green and red, since there's no yellow light after red? It's after green that there's a yellow light?
Yeah, it goes green, yellow, red, and then green again.
But I get the logic, like the logic is sound.
It doesn't go red, yellow, green?
No, you don't need to slow down after you're already stopped.
Ah, so this is what I mean by weird Montreal lights. Any other city?
It does go like that.
So I think maybe I'm thinking of driving in Britain, because if you have a red light in Britain, the yellow light comes on saying get ready to start. And then it
Really?
turns green. Yes,
Yeah.
it's absolutely true. And that's
What?
yes, it's only in weird places like Canada that they have this bizarre thing of let's just take off without any warning and kill the pedestrians.
Yeah, I just checked. According to Google, the UK does have that system.
Yes,
No way. Do you also get yellow after green?
yes,
Yeah, yellow comes both ways.
yes.
Well, that's pretty smart, actually.
Well, I mean, this traffic system in Montreal was designed for homicidal maniacs, as far as I can tell. And yes, Justine, you were quite right. You don't have to slow down if you're already stopped. But the point is, the interpretation of yellow is not slow down. In Montreal, it seems to mean accelerate like crazy now.
Yeah, that's always the question they ask in the driver's test. They say, what are you supposed to do in a yellow light? And people always get it wrong because they say accelerate when it's actually stop.
Yes, yes. Well,
It's a
personally, I
classic.
think this whole city needs to have a driver re-education camp or something.
If
Anyway,
only computer scientists could do that. Then the city would
okay,
be better.
let us move on. And so we're describing system of traffic lights in the UK. Okay, so the whole point of the red, yellow, green is that you kind of get ready, you check, are there any pedestrians still lingering along, before you take off. All right, and now the more complex one. Red. If it's red, then in the next state, it either stays red and it'll keep staying red until you eventually reach yellow, and then it will stay yellow until you finally get to green. So this is, I'm sorry, I forgot that this is not what you're used to, but this is how traffic lights work in places where they actually care about pedestrians. All right. Good. So, yes. So maybe we'll take a short break now and we'll restart at 12:05. So that's 13 minutes.
Can I ask a question?
Of course. Can I ask you a question first?
Sure.
How do you say your first name?
It's Henley,
Henley. Okay.
but I accept any kind of polymorphic variations of that.
No, but I've been saying it wrong, right? I'm saying Haneli all the time. It's Henley.
That also works. Like I said, polymorphic variations of sound are fine.
Yeah, well, I don't tolerate Prakash. It has to be Prakash.
I have a quick question about the use of linear logic. You mentioned that.
No. Sorry, time out. This is not linear logic. This
Yeah,
is.
that's temporal logic, but I would like to ask a question about linear logic. If you don't.
Okay, sure. Go ahead.
So I read some papers using linear logic, and they have all sorts of different operations.
Yeah.
Is this possible to combine these two logics? Because I see that if you want to express something that's concurrent and can be also parallel, it would make a lot of sense to combine both. Or
Well, the linear logic guys tend to be purists. They consider any other kind of logic to be bullshit. So
okay.
they will react violently if you do that. I mean, my own inclination is to be conservative about enriching logical things. I think temporal logic is great because it's kind of a minimal extension that really captures time. Linear logic is fantastic, but it's beautiful as it is. I don't really want to add new things to it. That's my feeling.
Okay. Point taken.
So you may know a paper written by Andrew K., Francisco Ferreira,
Yeah.
myself, and Brigitte in Popple.
Yeah,
And
the React system.
we used temporal logic as a type system for concurrent programs. Why is this thing moving by itself? Okay. But yes, linear logic, it is something we can talk about endlessly some other time. Recording, resume speaker view, share screen. Share, screen mirroring. Yep. Come on. Okay. What was that? Okay. I just want to introduce the notion of a labeled transition system. So we can see some kind of connection with automata theory. In a bit, I'll make that connection a bit more precise. So what's a labeled transition system? It's something a bit like an automaton. So it has a set of states. Again, now not necessarily finite anymore, because we're not thinking about computable power, we're just modeling behaviors. We have a set of actions. We have a labeled transition relation. We have a set of initial states. And now we have a set of atomic propositions and a labeling function. So S is states, perhaps infinite. Act are actions. This is a transition relation and it's ternary. But instead of writing S, A, S prime in this relation, which is of course how you should write relations, we will write S goes to S prime while performing an action A. I are the possible initial states. So this is not so much automata theory as system modeling. AP are some atomic propositions. And L is a function from S to 2 to the AP. So this is called the labeling function. And the point of the labeling function is that it tells you what things are true of a given state. So Label transition systems are used to model, for example, a program or a concurrent system of multiple programs, threads interacting and communicating and so on. So a run of the transition system is a sequence like this. S0, A0, S1, A1, S2, A2. Where S0 is one of the initial states, AI are all actions, SI are all in S, and at every index, SI, AI, SI plus 1. So this means it is possible for S to be in S1, perform the action AI, and end up in this next state of the run. So if you have that, that's a valid run. And a run basically describes the complete execution of one possible behavior of the system. So we'll also introduce, so at some point you might say, look, okay, we have these runs, but I only want to focus on the sequence of states. A path is obtained by removing the actions from a run. So then you end up with S0, S1, S2, S3. Okay. And finally, we'll introduce something called, we'll use the letter pi for a path. So whenever we say this is a path, we mean there was a run such that when you remove the actions, you got this particular path. You can't just make up any old sequence of states and call that a path. So basically a path describes one possible trajectory through the state space. And finally, so in fact, trajectory is a good word for alternative word for path. And finally, we define the trace. We'll define the trace of a path is going to be just what things are true. So it's going to be L of S0. So it's a set of atomic propositions that was true initially. So we can use trace pi as the semantics of an LTL formula. So it will be an LTL formula constructed from the temporal operators and using the propositions in the set AP that's given with the transition system. So we will say a path satisfies an LTL formula for what we really mean, which is the trace of the path satisfies the LTL formula. We'll define paths of S to be the set of all paths starting at S. and we'll say a state satisfies a formula. So we're kind of introducing two different semantics. If for all paths that start in S, you satisfy the formula phi. So in the homework, I've asked you some questions about construct a transition system showing that this thing is true or this thing is false, or these two things are not equivalent. So this is what it all means. Okay. So I'd like to show you a couple of fundamental formulas. So what does this mean? Supposing I say sigma satisfies this formula where P is some atomic proposition. What does this mean? So let's think about it. It is always true that P will be true sometime later. Okay, so let's imagine something like that. So you start out at the beginning and you say, yeah, sometime in the future P is true. Then you cross that point and you say, well, sometime in the future P has to be true again. So you cross that point and you say, sometime in the future P still has to be true. So this basically says P is true infinitely often. So this is a very fundamental thing. P is true infinitely often. So let's consider another formula. What does this mean? It's not a very good diamond, is it? There we go. Yes, what does this mean? I do have recording on, right? Okay, good. So this means after some point, P is always true. So basically this means P is cofinitely true. I.e. true always except for a finite set of places or finite set of times. Or there is some last time at which P is false. So basically it says you can wiggle around for a while, but eventually you have to settle down and then P has to be always true. Okay, So I'm going to show you some laws for LTL. So this is kind of coming to the proof theory, but I'm not presenting it in a nice natural deduction style. I'm just going to write down a bunch of equational laws. So circle, negation of circle phi is equivalent to that. Well, if it's not true that phi is true in the next state, then it's not true. Then in the next state, phi is not true, right? So there's a duality between diamond and box. So if it's not the case that phi eventually becomes true, that's because it must be that always phi is false. And if it's not true that phi is always true, that means eventually phi must become false. So I'm just saying these things like a preacher in the pulpit, laying down these laws from Mount Sinai. But in fact, you can check all these things from the semantics. Diamond phi is no different from diamond phi. And box phi is no different from box phi. I always want you to do this. This may have emphasis, but doesn't mean anything different from I always want you to do this. Phi until psi is a bit tricky. Phi until psi is the same as phi until psi. And phi until psi is also the same as phi until psi. Also, things like this are true. Diamond phi is equivalent to box diamond phi. And box phi is equivalent to diamond box phi. Okay, so this will allow you to simplify some things that might get otherwise too convoluted. And now we come to some super important laws called the fixed point laws. So I'll also do a bit of temporal logic tomorrow because I will add fixed point operators to temporal logic. But in order to do that, I have to first teach you some basic notions of fixed points, which I also need to teach you in order to explain bisimulation properly. So tomorrow, first some fixed point theory, and then bisimulation, and then fixed point extensions to temporal logic. But anyway, we can still already formulate some fixed point laws, which again, we can justify from the semantics, but I'll just assert them here. So phi until psi is equivalent to saying either psi is true right now, in which case there's nothing to check, or, well, we don't have to say or psi is not true, but this accounts for that case, or phi has to be true, and in the next time step, phi until psi holds. So you think of phi until psi as some kind of contract you signed. And how do you verify the contract? You say, well, is psi true now? Yes, then contract fulfilled. Or psi might not be true. Let's check this. Phi is true. Okay. And what's happening in the next step? Contract still valid. So the more simpler These are just special instances, but it's worth writing them down. Eventually, phi means either phi is true right now, or in the next time step, it will eventually become true after that. And similarly, box phi is phi is true now, and in the next time step, box phi will still be true. Okay, so these are the fixed point laws. And then there's the distributivity laws. So it says, in the next time step, phi until psi is the same as saying either in the next time step phi is true, not either, until that. And now two very important laws. Diamond phi or psi is diamond phi or diamond psi. And box phi and psi is box phi and box psi. You notice a kind of inversion. The diamond goes with or, the box goes with and, but you can't actually mix them. Diamond phi and psi is not equivalent to diamond phi and diamond psi. And box phi or psi is not equivalent to box phi or box psi. So why are these not equivalent? Well, this is saying there's some point in the future at which both phi and psi are true. But this thing is saying some point in the future phi is true, and also some point in the future psi is true, and there may be different points. In this thing, nothing is guaranteed on this side that phi becomes true and psi becomes true at the same time. Here, I am guaranteeing that. Conversely, this thing is saying it's always true that one of them is true. It might be that they're flipping. But this thing on the right-hand side is saying, no, either phi is always true or psi is always true. But this is guaranteeing neither one. It might be that in step 1, phi is true, step 2, psi is true, step 3, phi is true, step 4, psi is true, and that will still be okay for this, but certainly not okay for that. Okay, so these things are not equivalent. So we have always interpreted LTL formulas on infinite words. Or histories. So there's a close tie-up between LTL formulas and Bucci automata. So, which I won't spell out, but that's the kind of thing we do in the verification class where we prove that for every LTL formula, you can write down a Bucci automaton such that the set of histories that satisfy the formula are exactly the things recognized by the Bucci automaton. There's a very close tie-up between automata and temporal logic formulas. We can interpret LTL formulas on words. by i.e. finite words. So we'll introduce two predicates q sub a to mean the letter here at this position is A, and another that says the letter at this position is B. And then I can write formulas like this. QA implies circle QB. And this is satisfied by every A is immediately followed by B. So we can describe quite a lot of things in this way. What do we say at the end of the word? So circle next means in the next letter, false has become true. Well, this can't happen. So this is another way of saying there is no next letter. So this is how you signal the end of the word, and this is how you deal with finite words. And now you can ask a natural question. Okay, sorry. Given an LTL formula, phi, we define, I'll use this funky square brackets, to be the set of words such that the word satisfies the LTL formula. And now I'm thinking ordinary finite words. And we can ask a question. Is this always a regular set? In the sense of regular expressions that we have studied before. So now you see, once we've done that, we've got opened the door bit to automata theory and logic being connected. So if you're thinking about finite words, it's ordinary automata. If you're thinking about infinite words, it's Bucci automata. And many questions. So the whole paradigm now is systems engineers write down specs that they want their systems to satisfy in temporal logic. And in fact, experience, and this I'm now talking real software engineering experience, has shown that temporal logic seems to be natural for engineers to write down system specs. And now the whole thing is, okay, they write down a system spec and then they look at the traces of a system that they've actually built and they ask, does it satisfy an LTL formula? And so now you've got a relationship between automata and the specification language. And you want to say things like, I want to guarantee that this thing that I built satisfies your spec. This becomes a question about inclusion of regular languages. So now we have this thing about, is this set of words included in that set of words? And if they're both regular sets, this is now a straight algorithms question. So I pose this question to you. I give you an automaton, I give you a regular expression, and I ask you, are the set of words described, recognized by this DFA, included in the set of words described by this regular expression? How will you answer that? So I leave that for you to think about. But let's turn to this question. Is this always a regular set? The answer is yes. But you can ask another question. Is every regular set described this way? The answer to that is no. And so here comes your killer homework question of assignment 2. You have to prove that. Okay, so I've even told you what this set is. So let's say we describe something called odd P, or let's say odd A, which means every letter in an odd position is an A. That means, for example, A, B, A. Okay, so this thing satisfies odd P or odd A. Okay, any question about why this satisfies odd A? You see, this is position 1, this is position 3, this is position 5, this is position 7, this is position 9. And you see, every time I look at those odd numbered positions, I see an A. Okay, is that clear? Anyone asking a question? Adam, aren't we counting from 0 like usual? Yeah, sorry about that. I'm not, at least in this example. It wouldn't be difficult to modify it anyway. All right. So how do I write a regular expression like that includes exactly the strings? In odd A? This is last week's stuff. So regular expression, please, for odd A, strings like that. Notice I didn't say everything in the odd position is A and everything in the even position is B. I just said, I don't care what's in the even position. It could be A or could be B. So if anybody has a proposal, turn on your mic and tell me.
If we only have A and B in the alphabet, could it be
Alphabet is A and B.
okay? So then, A parentheses A plus B,
Mhm.
and all that start.
Good. So it was easy. Okay. But odd P is provably impossible to define in LTL. So that sucks. It shows a severe limitation of LTL, and that's your assignment question. Show that this is provably impossible. I think you would probably find it impossible to do this, but I've given you kind of quite a strong hint because I've outlined the way the proof should go. So how do we fix this? How do we enrich the power of LTL. And so one solution is add fixed point operators. To the logic. And this is a very subtle thing. So in order to explain this, I need to show you some fixed point theory. Okay, so I've been assaulting you with information all the time. I thought I will indulge in some light-hearted, not light-hearted, but some more kind of a survey of the territory type of remarks about how different logics fit together and how they relate. So we have at the very basis propositional logic. Very, very, very simple logic. We have soundness and completeness for propositional logic. So we know that something is provable if and only if it is a tautology. We have an algorithm to check for tautologies, namely what? What's the algorithm to check whether a propositional formula is a tautology? Okay, you draw the truth table. This is just a mechanical algorithm. And if you get all true for every combination, that is the definition of a tautology. So propositional logic is tautologies can be checked mechanically. Unfortunately, it's exponential because if you have n atomic letters, you have 2 to the n possible truth assignments. But be that as it may, propositional logic by itself has very limited use. The logic that most people use all the time is first order logic. So this is where you introduce predicates, function symbols, terms, and quantifiers, and individual variables. So instead of just P, Q, and R standing for propositions, you have X and Y standing for individuals, or N and M standing perhaps for numbers. So first order logic, it can be enriched by special symbols. So you can enrich it by saying, I have first order logic, and then I add the notion of equality to it. Or you can say, I take first order logic, and I add the notion of strictly less than to it, or both. And you can interpret first order logic also on words. Now you can ask, if I look at first order logic on words, how does it compare with temporal logic? So the point is, anything can be translated from LTL to first order logic. So for first order logic, we also have soundness and completeness. So there is a proof system which is sound. That means it actually only proves true things. And it also satisfies completeness, and it also satisfies compactness. So that's a big deal. By the way, LTL does not satisfy compactness. Oh God, I drew this in the wrong direction. So LTL does not satisfy compactness. And to see that, consider this formula, this infinite set of formulas such that every finite subset is satisfiable, but the whole thing is not. So let's say we look at P, circle P, circle, circle P, circle, circle, circle P, circle n times P, and so on. And in the end, not always P. So if I take any finite subset, then there's only some finitely many of these circles that can be included. And so I can find a sequence that satisfies all the circles up to then, but after that becomes false. So it doesn't satisfy box P. Okay, so any finite subset is satisfiable. On the other hand, if I take this whole thing, and this thing, since there's an infinite collection of these formulas, each of them is telling you P is true at every single point. And then this guy is saying, no, it's not. So this is a unsatisfiable set. So this is an unsatisfiable set. With every finite subset satisfiable. So this doesn't happen in propositional logic. It doesn't happen in first order logic. So then, now there's a very powerful thing called second order logic. So second order logic is, this allows quantifiers over functions and over functions and predicates. So you notice the principle of induction starts with, it says, for all predicates, blah, 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 blah. So even good old-fashioned induction on the natural numbers is second order. And so if you really want to talk about arithmetic is much more powerful than first order logic. So second order logic is super hard to describe, but there's a special restriction of second order logic. And it's called monadic second order logic. And this says the second order quantifiers can only quantify one-place predicates. So by the way, first order logic itself is undecidable. The validity of formulas in first order logic is undecidable. This will be one of our grand theorems in week 4. I will prove there is no algorithm that can take a formula of first order logic and tell you whether it's valid or not, where valid means true under any interpretation. Second order logic is even much worse than that. However, magically, monadic second order logic is decidable. And all the modal logics are actually fragments of monadic second order logic. So people have studied different kinds of modal logic, not just temporal logic, and basically they all live inside monadic second order logic. And the fundamental theorem proved by Bucci is that a set of omega words is omega regular if and only if it can be defined by a formula of monadic second order logic. And this started the big connection between logic, automata, and now has been expanded to games. So there's a three-way connection: logic, automata theory, and games. And lurking in the background of the automata theory, there's always algebra, because people like Schütz and Berger proved the following unbelievable theorem. So call a regular expression star free if you can write it without star. Now, of course, in this framework, we allow complement. So for example, you might want to write sigma star. And you say, how can I write that without using a star? But actually this is equal to empty set complement. So that's star free. Okay, so it's not so obvious what exactly is star free. And if you find, you can cleverly use some concatenations and some complements and write it without using star. So now it becomes not so clear. When can I mean, somebody might write something with a star, and you might think, maybe if I'm clever, I can write it without stars. So theorem, this was proved by Schütz and Berger. a regular language is star free if and only if its syntactic monoid so the syntactic monoid is the monoid you get by taking sigma star and quotienting it by the equivalence relation defined in question 4 of your assignment. Okay, so that's the syntactic monoid of a regular language. So his theorem says you look at the syntactic monoid, and if it has a certain property, its syntactic monoid does not contain a subgroup. So just because a monoid is not a group doesn't mean some substructure of it might have a group structure with an inverse and everything. Maybe the whole set doesn't. So the the whole syntactic monoid might happen to be a group too. But he proved his theorem. If and only if it doesn't contain any embedded groups, you can have a star-free expression. As soon as you have a group sitting around inside, you need a star. This is a remarkable thing because it's hard to see what's the connection between the algebra and this syntactic notation. Okay, I think I'm 1 minute past time, right? So I will say an end to this lecture. And next class, we will do start with some lattice theory. Then we will do bisimulation. And in the end, I will talk a little bit about what? Oh, yes, LTL with fixed point operators. If I don't get to that, I'll do that on Thursday, because Thursday, the only thing I have scheduled is learning automata, which is rather a light thing, may not require more than an hour. Okay, so cheers, goodbye. Have a good rest of the day, and I'll see you tomorrow.
All right, thank you.
Thank you, Professor.
Welcome.
Thank you, Prakash.
Bye.
Thank you.
Thank you, Prakash.
I'm supposed to do stop sharing.
Actually, I have a